Section 1.2 is about the properties of real numbers. Let's start by discussing what a real number is. It's a number that you use in everyday life. Basically, a real number is almost anything that you can think of, and it's made up of some other types of numbers that you've seen in the past. The first one is rational numbers. If you remember, a rational number can be expressed as a ratio. That's a fancy word for a fraction. So if you can write a number as a fraction, it's considered a rational number. It's also rational if the decimal is terminating. That means if the decimal stops, or repeating. And here you see some examples. 1/6 is a rational number because it's a fraction. 1.9 terminates, so it's a rational number. 2.57 repeating is rational, -3. Square root of 4 is really a 2. That's a rational number, and so is 0. There are other groups of numbers that you've learned in the past. There's the natural numbers, also known as the counting numbers sometime. They start with 1, and they go on forever. Whole numbers are exactly the same as natural numbers, but they include the number 0. And then finally, integers are the whole numbers, but they also include the negative whole numbers. If you have a number that is not rational, then we say that it's irrational. Specifically, it's irrational if the number neither terminates nor repeats. So if the number goes on forever in any way without repeating, we call it irrational. Here are some examples of irrational numbers. This diagram here is called a Venn diagram, and it's a graphical representation of the numbers that we just looked at on the previous slide. It shows us that the whole numbers, the natural numbers, which we're going to call capital N, are here, and they are a subset of the whole numbers. So they're inside the whole numbers. Whole numbers include 0, so it's going to be a bigger set. The integers are the z, and they include all the whole numbers. And then the rational numbers are the q numbers, and they include all the integers, the wholes, and the naturals. The irrational numbers are the ones that are not rational, so you see they're here in green. And then finally, the real numbers include everything. So this is a graphical representation. And it also gives you the capital letters that we use to describe each of the sets of numbers. Now these instructions tell us to name each set from which the number belongs. So let's take a look. Square root of 16 is a 4. So which one of the sets does 4 belong? Well, let's start with the smallest one. It's natural, because 1, 2, 3, 4. It's a whole number. It's an integer. It's not irrational because it's rational. It can be written as a fraction. I could write this as 4/1. So therefore it's a fraction. It's a rational number. And then it's also included in the real numbers. So the number 4 belongs to all 5 of those sets, and we list them by using the capital letters here. How about -185? Well, it's not natural because it's negative. It's not whole because it's negative, but it is an integer. It can be written as a fraction, so it's rational, and it's also going to be real. Square root of 20 is a decimal, and if you put it into a calculator, you get this decimal. And because it's a decimal, it's not natural, it's not a whole, it's not an integer. It does not repeat, so it's going to be an irrational number, and if it's irrational or rational, it's going to be a real number. Now if you notice, any number that you can think of is going to be a real number. This one, it's not natural because it's a fraction. It's not a whole, and it's not an integer because integers can't include fractions. But it is a rational number, and it is a real. The last one is a decimal, so it's not natural, not whole, not an integer. It repeats, so it's going to be rational and real. On this slide, we're going to review some real number properties that you use all the time in algebra, and we're just going to give them names and review what they mean. The first is the commutative property. The commutative property for addition and multiplication says that you can change the order in which you write numbers, in this case a plus b, and that's the same as b plus a. So the key word with commutative is it's about the order in which the numbers are written. And there's one for addition and multiplication. Notice there is no commutative property for subtraction or division. The associative property is about the grouping. And as long as you're grouping all addition or all multiplication, it doesn't matter which two numbers you group together and add first or multiply first. The identity property is about starting with a value, in this case a, and adding a 0 to it and keeping the a. Likewise with multiplication, you start with an a and you multiply by a value, in this case 1, and you keep the same value. So the identity is about starting with a value and keeping that same value. The inverse property is what number can you add to an original number to get a 0, and what number can you multiply by that original number to get a 1. And those values are called inverses, and we'll talk about those in a minute as we do an example. And then finally the distributive property. You've all done that. You take the a on the outside and you multiply it by each term on the inside, and you distribute, and you're allowed to drop the parentheses there. So let's take a look at what properties are illustrated here in this first example. I see a 5 plus 7 in parentheses and a plus 8. On the other side of the equal sign, I see the 8 first and then the 5 plus 7. Now to me that looks like I just flipped sides, so that's an order. So this is representing the commutative property of addition. In the second example, I'm multiplying 4 times x. But then on the other side of the equal sign, I move the parentheses to the 3 times 4 to multiply those first. That's a matter of changing the grouping. So that's going to be the associative property. And that's of multiplication. Down here, I want to find the additive inverse and the multiplicative inverse. Well, it would help me here if I rewrote this as an improper fraction. This is going to be negative 7/4. So what number can I add to negative 7/4 to get a 0? Here's the 0 that I'm looking for. And the answer would be a positive 7/4. So there's the additive inverse. And then what number can I multiply negative 7/4 by to get a 1? And if you remember using reciprocals, you're going to take the fraction and flip it. So if I multiply those two numbers together, I'll get a 1. Up here I'm getting a 0. So my multiplicative inverse is negative 4/7. Second example, 1.25. What can I add to 1.25 to get a 0? The answer is negative 1.25. So that gives me a 0. So that's my additive inverse. And then what can I multiply by 1.25? The answer would be the reciprocal of 1 over 1.25. Now you could leave that as a fraction, but typically we don't write fractions as decimals on the bottom. So if you put that in a calculator, you find out that that number is actually 0.8. And so that would be my multiplicative inverse. Here's an example which we're asked to simplify. We're going to use a bunch of the properties that we just reviewed on this slide, but typically we don't even realize that we're using them. We know how to simplify, and we're going to do that here. Start by distributing the 2, so 10m plus 2n. Then we'll also distribute the 3 to the second set of parentheses, plus 6m, and then negative 4 times 3 is negative 12n. Now we could technically use a commutative property to reverse the 2n and the 6m and flip their order and then group them together, but we don't need to do that because we know how to collect like terms. We know that if 10m and 6m are together in one expression, you can combine those to be 16m. Now that's technically the commutative and the associative property working together. And we also know that a 2n and a negative 12n can be combined to give me a negative 10n.